Hi, Daksh. Can you hear me?
Nishant, yes, I can hear you. Can you hear me?
Okay, yes, I can. Yeah, I'll just have a few slides on introducing OffNote Labs and then I
Sure. Yeah.
give it to you. Hi, guys. Good morning in India and welcome to this OffNote Labs talks. This is part of series of our talks where we invite external speakers from industry to talk to us, share their knowledge about very interesting cutting edge topics. And yeah, today we have Daksh Varshneya from Rasa, and he'll be talking about building better task-oriented chatbots for assistants. Um, so, so I'm going to wait for maybe 5 more minutes. I'm the founder of OffNote Labs, Nishant, and I'll just introduce quickly what our platform is, and then we'll start the talk. I'm just waiting for say few minutes and then we'll start. Yeah, so we have quite a few registrants for this talk, and you see people joining in slowly. So, I'll just start. So OffNote Labs is a is a platform for helping young researchers learn to research. So normally people have one slogan. We have two of them. You can pick whichever one you like more. It's a home for independent researchers and builders, and senior researchers will help young researchers grow and stand out. So these are both are part of our goals. So, like I said, it's a platform for individuals to learn to do research. There's no kidding or no PhD involved here. And the okay, why would you want to do research? Uh, so normally, your undergraduate curriculum or even several corporate jobs don't really let you flourish in uncertainty, deal with uncertain problems, open-ended problems, um, um, which which are essential for you to develop your problem-solving skills, do things of your own taste, and aim for impact. So research, which normally requires several years of PhD commitment, uh, allows you to do all of that: explore yourself, flourish in uncertainty, discover your own problems, and aim for impact, the kind of impact that you individually want. And so this program is is a sort of simulation of the PhD or MS PhD program, if you will. It's of a shorter interval, it's more intense. There are no specific topic constraints that we work on problems. It's all problem oriented. We pick a problem and then try to do research, read papers, implement stuff, and eventually try to publish. And so, yeah, we pick a problem of your taste and and progress with that. And why now? Why the time is right? Because the knowledge, scientific knowledge, is abundantly available online, uh, unprecedented at an unprecedented scale, and there is a rapid increase in eager and young learners who are absorbing the stuff by themselves, trying to build interesting stuff, trying to grow, trying to dig deeper. Essentially, they're trying to, uh, you know, do a deeper version of research all by themselves, and that is great thanks to this whole democratization of knowledge. But the issue is that when you are a young self learner, there is only this far you can go by yourself. You need the right people to mentor you so that you can get rid of your blocks and move faster. And so that's what our goal is. With mentoring, it becomes easier to go farther and deeper and do much more impactful research that otherwise you'll be able to do. So that's young researchers and mentors, and this platform which we welcome both of them. There are a number of young researchers who are part of the platform. They have delved into research, read papers, built stuff. Some of them have even published their work in a premier conference. And we invite more of them who are eager to learn, do research, and become experts in when you haven't been exposed to research, it's a very vague concept in your head. But as you, with mentoring and with with a guiding problem, you learn, what it means to become an expert and have your own individual research. And research is not equal to just reading papers and doing academic stuff. It involves building stuff and building a software which people use. It's all open source. That's our motto. And yeah, and all of it involves pushing beyond your comfort zone. So that is something that not many people are used to. Only in specific environments, maybe startups, people push themselves. So this is an intense program, and we welcome mentors who are mentors. Normally, working research labs have lots of constraints on what they have to work on, or the time-bound limits. At OffNote Labs, we are free to pursue open research with very little constraints and problems they're passionate about, open-ended, and they enjoy mentoring. So we need some of your time so that you can help young researchers learn and grow. And obviously we invite mentors to give talks, to share their journey and learnings. All the mentors started off as undergraduate students and figured out their research journey with time. So we love to learn from them. Okay, so that's it. Follow us on LinkedIn, Medium. We are growing. As I said, the number of researchers part of the lab, and they've done interesting research and built interesting tools, and we are growing. We hope to build many more impactful open source tools and publish research. So please spread the word, help the right people reach us, and help our platform flourish. And thank you so much for joining this morning in India. And if people are in different time zones or night, thank you. Really, thank you for joining. Now, Daksh will as I said earlier, Daksh, we are very happy to have Daksh Varshneya from Rasa to talk to us about building task-oriented assistants. And now Daksh will take over. I'll stop sharing and just briefly introduce. If you want to ask a question, there's a chat box and there's a raised hand icon. So if you click the raised hand, I would be able to connect you to the mic and you can ask, or your chat box. I'll be monitoring the chat box. So if you put your question there, I'll periodically send them to Daksh and he'll be able to answer it. Great. So thanks.
All right.
Yeah. Daksh.
Thanks, Nishant. Can you folks see my screen? Is the screen visible?
Yes, I
Okay, thanks. All right. Hi, good morning, good afternoon, good evening, wherever you're joining in from. I'm Daksh, machine learning researcher at Rasa. And today we're going to spend some time just talking about how can we build better task-oriented assistants, what are some of the recipes that we've found, we've researched about, and that we feel, let's say if you're getting into the space of conversational AI, or if you're building assistants yourselves, all of these things would be good for you to know to make progress much more easy for you. And by no means this is going to be an exhaustive list. As I said, these are just some of the things that I felt would be important for you. All right, so just a brief introduction. I did a integrated master's course in computer science graduated in 2017. And my specialization was in data science, and much of my research work was in the field of computer vision and sequence modeling. Post that, I joined a startup named Aganita back in India, in Hyderabad, and I was working on a large variety of B2B AI solutions spanning across NLP, computer vision, and speech processing. So problems around document retrieval, image segmentation, speaker separation. So quite a nice variety over there. And post that, I essentially joined Rasa as a machine learning researcher, where I'm focusing a lot on NLP now. And much of my research interests are now towards just representation learning for dialogue, and essentially exploring generative models for a lot of different tasks, quite tailored towards, again, dialogue. And apart from this, I'm also a fun-time co-founder at a platform called NewsLab. It's essentially a platform to help news providers build podcasts and generate podcasts at scale and give them more visibility in the market. So if you're interested, if you're curious, go check out the website, newslab.ai. And of course, that's me. I love sunsets. So just a small introduction over there. All right. So anywhere, as Nishant said, if you feel like you have some questions, please feel free to interrupt me and ask them at that point. So just to set the context, what we really do, we want to build the right amount of tools, what we call as the infrastructure layer for conversational AI, which should help a developer with minimal amount of machine learning experience to build assistants that can really work at a large scale and that can scale to real world conversations. And the way how we do it is or we build open source framework, we build open source tools to assist our users, and essentially because of that we have a community which drives those open source tools forward. And to improve these open source tools, we do a lot of applied research which essentially improves a lot of the algorithms and tools that we have in the open source framework. um, and and for folks who are not very much into text assistance, just for context, let's say, so when we talk about task oriented assistance, one way to solve it, and this has been really a conventional way to solve task-oriented assistance, is through taking a modular approach where you break your task-oriented assistant into two modules. One is the natural language understanding module, and the other one is your dialogue manager. So, for example, let's say you can have an assistant where the assistant asks you, would you like a medium or a large pizza? And as a user, I could say a large one, please, right? And so so how the modular framework would work is that it would first take this message of the user, break it down into more structured information, which is intents and entities. So intent is essentially what is the intention of the user that they're trying to express. So over here, they're trying to order a pizza, and in the same message, they're also trying to specify an entity, which is what is the size of the pizza that I want to order. And once that is done, then that's when the dialogue manager kicks in. And what the job of the dialogue manager is basically to look at the context of the conversation, look at the most recent turn, and based on that, take the most appropriate action for the assistant. So in this case, for example, the most appropriate action would be to ask what if you want some extra toppings, and that's essentially what the assistant would do, right? And um, we're going to focus much on the natural language understanding part today. All the questions that we would try to answer would be around natural language understanding. We can do something similar for dialogue management, but I definitely feel that's a separate talk in itself. So let's keep in mind that everything that we discuss is for natural language understanding today. Other than this, some of the recent work around building task-oriented assistance is also a more like an end-to-end approach, where you do not have an explicit natural language understanding module. Rather, you essentially take the message of the user, directly ingest it into a machine learning algorithm, and the model would predict the best response directly from the user message and looking at the context or the history of the conversation. So again, that's again not our focus. We're right now focusing on modular task-oriented assistance and the natural language understanding part of it. All right, so let's take a look at what are we trying to answer today. Essentially, when you're starting to build a task-oriented assistant, for the first question that we can ask ourselves is what's a good pre-trained encoding scheme or a good pre-trained encoder that can work specifically for dialogue tasks, right? Because there are so many pre-trained encoders which can give you word representations, sentence level representations. So a good question to ask first is what kind of encoders can work well for dialogue tasks? And then a follow-up question actually is to take a step back and say, really, are pre-trained encoders always the most effective choice? And can we maybe not get caught up in using large-scale pre-trained encoders, which might affect the latency of an assistant? So are there better choices that we can make over there? And once, let's say, we've made our decisions on how do we want to featurize dialogue through these pre-trained encoders or some other featurization scheme, There are definitely some cues that we can take from different other domains around data augmentation to squeeze out more of our current models. So we'll try to look at one such data augmentation technique, which we call as paraphrasing, and we'll see how that can help to squeeze much more out of the current models. And lastly, we'll then see what are some of the best practices to while building an assistant. And one of the best practice, or one of the practice that will always help while building an assistant is how do you enable this concept of continuous learning for an assistant, which means as in when your assistant is deployed in the real world, it should be able to look at real conversations that's having with real users, and consequently learn from it and improve itself, so that some conversations that do not work today, they can work, tomorrow or in the future. And just to lay out, essentially the questions are in an order where the first few are a bit more research heavy, and as we go forward, the next few would be basically more around best practices. The way how we would like to structure it maybe is this is around a 90-minute talk. So we'd like to have, maybe the first two questions in the first 40 minutes, take a 5-minute break, and then let's say come back to look at the next few questions. And then I'll obviously leave some time for questions that might come up later. All right.
So,
So
if I can interrupt, there's one question from Harishankar.
yeah,
You mentioned end-to-end approaches. Can you give some pointers on them?
sure. So when we talk about end to end, let me come over here. So when we talk about end to end approaches, the way how current research is going about it is more into solving open-ended dialogues first by end-to-end approaches. So what you do essentially over there is take, let's say, a language model or a language generating model, which is like something like GPT-2, if you're aware of it, and you feed in, what you do is you basically feed in the whole conversation as input to your model, and you then want the model to generate a reply, and it should be a coherent reply to whatever the user query was. Now, the reason why I say open-ended assistance is because these models are really just trained on data that is mined from the web, and they're not really tailored for a particular task. And tailoring them and making them work for a particular task is itself a hard one, because when we talk about these large generative models, one aspect that has to be much worked upon is how do we control the generation of these models? How do we do more control generation so that it's able to narrow down its scope, right? So um, which is why I don't see right now, as of now, how end-to-end approaches can, really build production level assistance. Because first, you essentially don't have much control over them, right? When you break down things into modules, you can actually more manage them much better. Second, you're relying too much on just a language model to generate language for you. There are so many risks associated with it. For example, profanity, bad language, and because these assistants can be trained on large scale web corpuses, there's so much wrong text that's out there over there. So from that perspective, end-to-end tasks, end-to-end assistance are some things that are actually coming up gradually. And if you're interested, there is a model called Dialog GPT. You might want to take a look at that. And otherwise, we're also working towards end-to-end assistance and seeing how you can do that in conjunction with modular assistance, essentially. So, all
Yeah,
right.
sounds good. Thanks. Yeah.
Cool. Thanks, Nishant. Okay, so the first question, which is how do we evaluate different pre-trained encoders that should work best for our dialogue tasks, right? And just as a reminder, the dialogue tasks that we are right now focusing upon are intent classification and entity extraction, which make the core of natural language understanding for an assistant. So one way to try to answer this is, let's try to motivate what do we really want representations from these encodings to capture. And let's try to motivate it through an example. So for example, let's say if a user comes in and talks to an assistant and says, get me an appointment for tomorrow, right? Now you would say the intent over here of the user is to book an appointment, and at the same time, the way how they have expressed their intent is called what is known as dialogue act. So the dialogue act for the user at this point is, it's a command. It's more like a command. It's like an imperative statement where the user has said, hey, do this for me, right? Now, another way of saying the same thing is through asking a question, which is, can you get me an appointment for tomorrow? Now, the intent is the same, but the dialogue act has changed, right? And what this essentially does is that if you really want your assistant to be as natural sounding as possible, you really want to tailor the responses of the assistant to the dialogue act that the user has expressed. So in this case, since this was more like a command, you would say, okay, here are the available timings, right? And then this was a question over here. You would say, all right, you would first want to acknowledge the question. Yes, I can help you with that. And here are the available timings, right? So based on the information that we're able to extract, the different kinds of attributes from the user message that we're able to extract, we want to tailor our responses and get our assistants to respond better. And if we abstract out a bit, essentially the task of intent classification falls under a category which is around semantics, and dialogue acts are essentially around a category called as what are called as pragmatics, which is basically these are two branches in the field of linguistics where you are and both of them are important essentially to make a conversation feel more natural. So while we saw that semantics or the intent classification task can be learned through supervised learning, right? Because you can always build an intent classifier. It would be better if these pragmatic cues, which are some things like dialogue acts, they can be picked up inherently by the representations themselves, because dialogue acts itself are not very well defined all the time, in the sense that you can be expressing a sentence or a question, and the same utterance could be expressing both a question, a command as well, right? So it's not very easy to categorize a dialogue act, and hence you would want the representations to capture different kinds of dialogue act that a particular utterance has. And that's essentially what we really want to evaluate. So we want to see how much do these representations from pre-trained encoders capture the aspect of pragmatics, because we believe that this is important for building better task-oriented systems. And to see that, whenever we start building a pre-trained encoder or whenever we start pre-training an encoder, right, there's this first question that comes up: what's the data that I want to train upon, right? So broadly, there are two kinds of data that we can look at. There's more conversational data, which are some things like Reddit threads where people have posted their questions, their reviews, their opinions, and essentially people respond to it with their opinions, answers, and essentially the whole. If you look at the text over here, this is more like a conversation, right? So the conversation would have both the elements of semantics and pragmatics over here. Whereas on the other hand, there is prose data, which is, let's say, articles from Wikipedia, articles from news websites, right? And the thing to note over here is that a lot of pre-trained encoders that we see in recent times have been pre-trained just on prose data, which brings in the problem that this prose data is missing pragmatic cues, right? So can we expect these pre-trained encoders to pick up any pragmatic cues? It's a question to ask in itself, right? And the hypothesis that we should start working off with is that, hey, if we, let's say, purely pre-train on conversational data, I'm sorry, I think no, one sec, let me present again. Okay. Yeah, so if we pre-train purely on conversational data, then maybe these representations pick up much more pragmatic cues, and can we evaluate that? So this is the hypothesis that we're going to start with, and let's see if we can evaluate that.
So I have a quick question. So when you say pre-training, it is pre-training for just like a masked language, or is it pre-training for generating response? Are you
Sure.
talking about both?
Sure. So I mean, as we define pre-training is just more general purpose training of a large encoder for a task which should be general enough and adaptable for different other fine-tuning downstream tasks, right? So a pre-training objective can be for just mask language modeling, which is trying to predict some masks that on the input side, or it could be for generating language like autoregress in an autoregressive fashion. So pre-training objective itself is a good topic to explore. But I would say right now, I mean, I would say really the first question is what is the data that we should be looking at?
No, so the point is that either of those pre-training objectives can
Mhm.
fit into dialogue generation task or reply generation task.
I
And
mean, definitely, but I think it's not necessary that your pre-training task should always be aligned itself. It can still be picking up a lot of things, that elements that you see in a conversation, but it's not necessary that a pre-training task is something like dialogue generation, because that's actually a downstream task for you.
yes, okay, thanks.
Um, so yeah, so just to investigate this, what we did was we started off with a data set, the first step that you do for any problem. And what we essentially took an annotated corpus of dialogue acts, and an annotated corpus of utterances which have these dialogue acts labeled. And we took a collection of 10 dialogue acts over here, as you see. And this is essentially a collection of around 1,300 utterances. And each one of these dialogue acts is a way in which you can express some intent to your assistant. And once we had that, we made up a list of candidate encoders that we want to evaluate. So starting with our good old friend glove embeddings. Glove embeddings essentially give you word level representations, and then going to more efficient sentence representations like the universal sentence encoder model, and then moving forward to our recent friend, which is BERT, the transformer based model. And then essentially the fourth and fifth are more narrow. They're actually more narrow models, which are, so what we did was we fine-tuned BERT on a conversational corpus, made that as one of our candidate models. And then there is this model called Convert, which was put out by a company called PolyAI in open source at that time. And this is purely pre-trained only on conversational corpus. So the difference between 4 and 5 over here is BERT is first pre-trained on prose data, then fine-tuned on a conversational corpus, and Convert is purely pre-trained on a conversational corpus. And the experimental setup that we started off with was, can we use unsupervised learning for intrinsic investigation because we did not want. So there are two ways how you can evaluate representations of an encoder. One is an intrinsic evaluation, another is what is called as an extrinsic evaluation. Extrinsic evaluation is where you use some proxy tasks to a proxy task where you use the representation for featurization and then pass it to, let's say, a task specific architecture, and then you evaluate the representation's quality on the performance of the downstream task. But intrinsic evaluations are more interesting because what you're really trying to do is you're trying to get deeper into the representations and trying to see what are those representations actually capturing. And hence you don't want to really test it on a proxy task. You really want to see maybe through clustering, see what are if you, let's say, if you cluster some of these utterances, how well can you bring out clusters and what do those clusters actually mean, right? So it's more involved, it's more qualitative at that point, I would say. So the experimental setup that we started off with is that we collected, as I said, I collected a corpus of utterances. We featurize each utterance with the candidate pre-trained encoder. We cluster these utterances, and then we try to see how consistent are these clusters with the human annotations of dialogue acts that we've started off with, right? And this begs for a question, which is, we're talking about clustering over here, which means what's a good measure of similarity for clustering? Because that's essentially what you need for clustering. So let's say if you have a matrix of featurized utterances, say X, the first thing that you can do is, hey, let's start with first order similarity, which is essentially a dot product of the matrix with its transpose. But is that enough? Because, the dot product may not be capturing just dialogue acts, right? Or may not be just clustering for dialogue acts, right? Because representations are essentially a vector of numbers, and these vector of numbers can be capturing a lot of things. So different similarity measures or different orders of similarity can bring out different attributes that these representations are capturing. So essentially the follow-up question over here was, hey, can we improve our similarity measure to just maybe explore higher orders of similarity or arbitrary orders of similarity, if you might say so? Maybe, second order similarity, where you just again take the similarity matrix and multiply it with itself. And to do that, we essentially came across this really neat paper from Mikhail's group. I would definitely encourage all of you to maybe go back and read this paper if you're interested. But in summary, a very neat trick, and I'll not go deep into the derivation, but what they showed was, let's say if you have the first order similarity, which you've defined as X multiplied by its transpose. Since this is going to be a real symmetric matrix, you can decompose this into its eigenvectors, eigenvalues. So eigenvectors is, let's say, the Q matrix, and then the lambda is your eigenvalue matrix. And what they showed was essentially you can define a linear transformation of the original matrix X. And this linear transformation is essentially a composition of your eigenvalue and eigenvectors, which is basically shown over here. So if let's say you set W to the eigenvectors multiplied by the square root of your eigenvalues, we can derive this out, but the similarity, the first order similarity of the transformed version of the utterances will be equal to the second order similarity of the original utterances. So, and what you can now do is you can now parameterize this matrix W by a constant alpha, and essentially if you keep changing now this alpha, you are essentially exploring different orders of similarity, because based on the value of alpha, the exact m or exact x dash that you get would keep on changing, right? So this is one way how you can essentially keep transforming your original embeddings into different projection spaces, and you are then hoping that at least some of these projection spaces are capturing the exact information that we are interested in. And then when you subsequently cluster these utterances, it's going to bring out the information that we are interested in. And that's essentially so we basically took this trick, applied our experimental setup, and that's what we saw. So a lot of
So
things.
if I can interrupt, in more intuitive terms, what
Mhm.
would first order similarity look like? Or if you can give two sentences and where you can describe what first order similarity means, what second order similarity means. Is there a more intuitive explanation possible, or
That's a good question. We did do some work into what exactly these orders can capture,
uh
but that's essentially what we are trying to see through clustering, right? Because we are looking at clustering as a way to surface what these similarity measures can get us,
nice.
right?
So when you
Uh,
view the clusters, maybe they help.
yeah. So we did some qualitative analysis on this, and but our focus at this point is essentially that we do not care about which order of similarity brings us the dialogue act information, but as long as it can bring up in some order of similarity, we are okay. Because let's say if there is a extrinsic task that we want these representations to work on, you can always expect a supervised learning model to search a projection space in which this order of similarity is actually present, right? um, so going back to the results, so what we found was that it's definitely models that are pre-trained or fine-tuned on conversational data, these pick up pragmatic cues much better than any other models. So the values that you see over here in the table are what are known as homogeneity scores. Without going too much into detail of homogeneity scores, these essentially measure these measure the entropy or the information gain after clustering. And how they work is you would have goal set of groups or annotations or dialogue acts in this case, right? So you have for each utterance what is the right dialogue act, and then essentially from there you know what are the groups of dialogue acts and what utterances get inside each group. And then there are some groups that your clustering is outputting. So homogeneity score is essentially measuring how homogeneous or how homogeneous one cluster is, which means one cluster should contain exact utterances of only one dialogue act, and it should not mix up multiple dialogue acts inside one cluster, right? So it's basically a quantitative measure for that. And what you see over here is these are essentially comparison sets, which are a set of one or more dialogue acts that we saw. And for each of these comparison sets, we try to cluster utterances from these dialogue acts and see the homogeneous score. And you see that the convert model, which was just pre-trained on conversational data, it exceeds any other model by far, right? And this was a good validation that yes, there's definitely some gain in pre-training on just conversational data and trying to come up with more efficient representations. Because um, talking about the convert model is a little out of scope, but just to put things into perspective, the convert model is also half the size of the BERT model. It's much more faster in terms of how transformer layers are composed of, and which basically shows that if you take the right data for the right domain that you're trying to solve, it's going to yield better results. And this is what this gave us the validation. And we also, of course, the story cannot be complete without any extrinsic evaluation, because this is dialogue. I mean, if we're trying to solve dialogue tasks, we took a direct dialogue task for extrinsic evaluation, where we took the task of response selection. So basically, response selection is somewhat similar or somewhat close to end-to-end assistance. So let's say if a user asks a question, the task for response selection is to pick the right response out of a candidate of responses, right? So you have, let's say, there's this question that can be asked to an assistant: what version of Python do I need to install Rasa open source? And there are candidate utterances for the assistant. The assistant should pick up the right utterance, right? So what we did was we featurized essentially both the user message and each of the candidate representations, each of the candidate utterances for the assistant. We took a dot product similarity of both of them, and we picked up the response which has the highest similarity for the task for the user message that has been received. And we learned one logistic layer on top of the representations to get one projection for the task at hand. And the measures, the metrics that we see over here are what are called as hit at k scores. So what this measures is how many times did the gold utterance come up on top or come up in the top k predictions. So hit at 1 is basically measuring how often did you get to the best response at once. And then hit at 3 would be how often did you get it in the top 3 responses. And over here again, you would see that Convert by far excels each of the models that we have. So yeah, that's
So
the thing.
yeah, and there are a couple of questions now, and I'll take them. Sorry, I hope I didn't.
Sure, go ahead, please.
Yeah. So I'll start with the most off the topic, or not really off the topic. Is Dialog Act supported in the latest version of Rasa, or it's still under research, working?
So dialogue acts, what we believe, as I said, is dialogue acts essentially help you to get to better responses, right? So how I really see dialogue acts is it should help in the case of end-to-end assistance, and that's something that we are working towards. How do we build better end-to-end task-oriented assistance, right? And if we are able to, and the first question essentially, that's why there is that, what is a good featurization strategy even to get to an end-to-end assistant so that it can respond with more natural responses. And that's where we feel dialogue acts will come in at that point of time. So right now, if you ask for modular task oriented assistance, I wouldn't say that we have that, but it's more in future work.
Future. And quickly, this is a slightly long question. For evaluation, you could train for fine-tuning task of simply classifying dialogue acts.
Yeah.
And compare different models based on the classification accuracy. Yeah. So
Definitely, that's a great question. The problem, but here's how we motivated the problem, right? Which is, let me go back over here. So as we said, intent classification.
so sorry, your screen is lost.
Oh,
The sharing is stopped.
oh wait, let me reshare the screen. Sorry. Is it visible now?
Now it's good.
All right. So as we said, semantics or intent classification is something that is more user defined. Dialogue acts, it would really be difficult if, let's say, we make a user of an assistant start annotating the dialogue acts as well for the training data, right? Because it starts to become a combinatorial explosion problem where you first annotate the intents for each example, and then you start annotating dialogue acts as well, because one intent can have multiple dialogue acts and things like that, right? So what we really want to measure is how good these dialogue acts are just captured by the representations itself, and the problem that we run into if we just test this thing on a with a classification based approach is that if you learn a layer or just a simple logistic layer on top of the representations for the task of dialogue act, there's no guarantee that all the numbers that you're seeing are just because of the logistic layer that you have, or because the representations themselves were good, right? So you can and that's essentially an evaluation that we were not very much interested in. We definitely ran them, and what we saw was, even training for dialogue act classification with limited amount of data is actually very hard. So supervised learning for dialogue acts is not an easy problem, because, as I said, one sentence, one utterance can have multiple dialogue acts in them. Does that answer the question?
Yeah, while he responds, there's a third question which maybe you can just quickly answer. Is second order similarity like transitivity relation between representations? Is there,
Um,
can it be viewed like that?
so second order similarity is definitely more about, I would say, something like you're looking at more compound attributes. So there are attributes that work at a surface form. So let's say if you're looking at a particular sentence, then each sentence has a syntax or a surface form representation, right? Now, this representation, the first order similarity will kind of capture the what are the different representations that are existing in your data set. And then the second order similarity would be more around, hey, let's say if I compose both the surface from representation and, let's say, semantics, and put them both together, what similarity do we see over there then, right? So these are more compound levels of similarity, I would say. That makes sense.
Thanks. Yeah.
Right, any more questions at this point?
Yeah, just to remind everybody in the audience, so you can type in questions in the chat. You click the chat icon on the right. You can
All right.
put in your question.
So
Well, one quick question came in.
yeah.
So Shashank, once you have figured the higher order similarity to validate your task, do you still need a supervised training?
Yeah, that's a great question. So I mean, as you see, you can come up, or you can find the optimal order of similarity, but then that's, I mean, in some cases that's okay if, let's say, you really don't want to build a dialog at classifier, as we said, right? Because if you don't want a dialog at classifier, then you might be okay with saying, hey, yes, these representations are capturing this information, as long as we need them for a downstream task, we're fine. But I would say supervised learning approaches would lead you to a much better stage if really the task is that you want to solve, let's say, dialogue hacks, and you will only want to build a classifier for dialogue hacks for some specific reason, right? In my opinion, I think supervised learning will have its benefits over there, but just to investigate what representations are there, I think this trick would help you out much more.
Okay, very quick. Is there a universal vocabulary for dialogue acts? Is there a standard So these are the set of data, or that keeps evolving.
So this data set where we took it from, this is called the switchboard dialog act corpus. This was essentially a collection of, I think, if I remember correctly, it was around 50 dialog acts, but it's not a universal, I wouldn't say it's a universal vocabulary. What we had to do was just narrow down the focus on some of the more important dialog acts that we felt, and for task oriented assistance, and dialogue acts which did not have a lot of noise in them. So we had to manually go through a lot of these utterances, clean up annotations for them. So yeah. All right. So just to summarize, I would say there is still scope for building much better pre-trained encoders, which are just tailored for conversational AI tasks. Convert, the model Convert was one such attempt, but unfortunately, it's no longer available in open source. The company which put it out in open source, they had to take it offline for some reasons. I'm not sure why, but that's really unfortunate. And so if you are getting into conversational AI research, this is one good area to really put down your head and see what we can do better over here. Right. So this leads us to the next question, and I think I'll take around 10 minutes for this before we break. And so the question essentially is that, let's take a step back and say you have these pre-trained encoders, but are they always necessary for solving the natural language understanding tasks that we have at hand? And can we maybe do better than just using these large-scale pre-trained encoders? So again, yeah, just to revisit, these are the two tasks that we are trying to solve. And I see there's some point missing. Sorry for the mistake in the slides. But what we really want to see over here is, what are some of the real world constraints under which an assistant is actually built, or a task oriented assistant is built, right? So when users start building an assistant, you have very limited amount of data to start with, because all of the data you might have to add manually. So you would come up with intents, and then for each intent you would list down some of the ways how your users can express that intent. And that's actually a tiring task, and it's not an easy task to start with. So you start off with very low amount of data. You have very domain. You can have very domain specific vocabulary, which means, let's say if you're building an assistant in the healthcare domain, then you would have very domain specific rich vocabulary. So and motivated from these two questions, we then essentially went to ask slightly more technical questions, where we said that, hey, what's a good baseline to start off with? And maybe a good baseline is still using our good old bag of words features, which are something like TF-IDF features, where you're essentially looking at the count of occurrences of each word in our input message. Can we build something around that, and can we benchmark them against these pre-trained encoders? That was one. Then we started looking at, hey, are intent extraction and entity extraction really independent of each other? Can they benefit from each other? Because you can imagine that there are some entities that can exist only inside one intent. So there's definitely some dependence between them, between each of them. And maybe models can benefit from knowing annotations for both of them at the same time. And then the third comment is more like a tongue-in-cheek comment, but because we always necessarily need 12 layers of transformer to solve an NLP task? Can we do better? Can we build more lightweight models? And I'm stressing on lightweight models because when you're in conversational, when you're building assistants, one aspect that you have to think about is latency and throughput of the assistant. And these large-scale models will slow you down to a large extent. And that's essentially where we designed our next architecture, which is called DIET, which is dual intent entity transformers. And you might say there's a lot going on in this picture, but let's break this down into smaller parts. So let's just understand what are the different, what's the thinking behind the architecture and see. So the first thing is, let's say you have an input message, right? Let's say something like play ping pong. And You can ignore the mask over here. I'll come back to it, but let's assume that the message is play ping pong, and that's what we want to feed to our model. What we do is we first feed each token by token, and we featurize it through two kinds of representations. One are what we call as sparse representations, and the other is what are dense representations. Sparse representations are essentially your bag of word features, the count vectors of at a token level or at a phrase level. And then you would have you can also use some word level embeddings to featurize them. And then, because these are essentially, more often than not, these sparse features would be one hot encodings, you pass it through a feed forward layer, or you may call it as an embedding layer, and just construct some dense representations for these sparse features. You concatenate both of them, pass it through another feed forward layer, and then you pass it through a stack of, let's say, two transformer layers. Now, and so you do this for every token. And what you do next is you take, on the input side also, you take an extra token, which is, let's say, a CLS token. Essentially, this is how sentence representations for transformers can be captured, where you add another token, you featurize it in the same way, and you take the representation of that as your sentence representation. So you take that as the sentence representation, pass it to an embedding layer. You can call it a projection layer as well. But the idea is you're trying to now embed the whole sentence into in one space, in an embedded space. And parallelly, what you do is you also take the intent label with your intent label, pass it, you featurize it through a one-hot encoding, pass it through an embedding layer, and you take the similarity of both the sentence representation and your intent label together and try to learn a shared embedding space over here. Right? And you pass the similarity to a loss, which is essentially nothing but a dot product loss. So the way how this dot product loss works is, at a high level, it tries to maximize the similarity of between the positive pairs of input sentences and your goal label. And it basically minimizes the similarity between negative pairs of your sentence and any other label that you can sample for this sentence, right? Now, I mean, when I say sample, these are really negative labels, essentially, right? So that forms your intent loss. And then, so over here, what we saw was we basically combined lightweight bag of words features with some, if you want, some pre-trained embeddings. And all of these are modular in the sense that you can choose to use any of the pre-trained embeddings, or you may just leave them out. And then for the task of entity extraction, you pass the representation of each token to a CRF layer, and those representations essentially go to a loss that's tailored for entity recognition. It's basically the CRF loss, and you add both of them to learn a joint model for both intent and entity extraction. And coming back to this mask, what we also saw was, the hypothesis that we started working was that one more efficient way of learning surface from representations of what is visible in the data is just to have the model predict or reconstruct masks from the input. So basically, you input a mask token, and the job of the model is to predict what could be that mask token, right? So you take a similar approach where you input the mask token to the transformer, take its representation, embed it in a shared space where the embedding for the actual token is also present, and you take the similarity measure, feed it to a mask loss, which is very much similar to the intent loss, and add that as well to the total loss. And this is how we essentially fed, we basically incorporated both intent classification, entity extraction, and some lightweight featurization as well. And we found some good results. So starting off with results on some benchmarking data sets, there's this data set called the NLU evaluation data set, where the previous state of the art for both intent classification and entity recognition was around 87 and 87 each, I would say. So let's say let's look at the F1 scores. And what we found was diet with sparse level representations and convert representations as your dense embeddings does much better than the state of the art. It's at least 3 points higher than what we have for the previous state of the art. And what we also wanted to test was, we started off saying, hey, can 2 transformer layers do our job for the task that we have at our hand? And the real reason why we wanted to test this was that there are a lot of recent works who've just used something like BERT, a BERT model, heavyweight BERT model, fine-tune BERT model end to end, and solve the task of intent classification and entity recognition. And the intention over here was to just show that you can get off with a much more lightweight model. So a fine-tuned BERT model achieves almost similar intent entity score as you have for diet with sparse and convert features. But the point to note over here is diet is 6 times faster to train than fine-tuned BERT, right? And that's a huge advantage, I would say. And then on the right hand side, what you see is essentially how does the performance of diet change with different representations on the input side. So this is, the table basically shows you different combinations that we tried out. And one takeaway that I would really like to stress upon is, we started off with this question: can we build a baseline model which has only sparse features and is still competitive with state-of-the-art models? And the first row essentially shows you that. So taking only sparse features and no dense representations, no masking loss as well, your intent classification is just 2 points behind or 3 points behind the state-of-the-art. And entity is again just 3 points behind. So that gives you a good validation that sparse embeddings, or just count vectors, featurizers, they are still a very strong baseline to start with, especially when you're just starting to build your assistant, because you have limited amount of data, and a lot of those words can go out in they can basically be out of vocabulary words for your pre-trained encoder, and that will not help your model in that case. And with that, I think that's the end of the second question. Yeah. So any questions?
There are a couple of questions, and I'm not sure what is the right time to ask now, because and you again lost the connection. So you are sharing as.
I'm not sure why that happens, but let's see.
There's a break in connection.
Can you guys see it now?
Yeah. So sparse encoding is an interesting observation. So can I infer that mostly it's specific words that count? That if you have those specific words, then the intent is probably straightforward, can be inferred straightforward in most cases.
Yeah. That's definitely one of the motivations. We definitely feel that intent classification is not such a difficult task that you really need a very high, very difficult, very sophisticated sequence modeling over there. Even without transformer layers, we've done a lot of experiments where the transformer layer is just deleted over there, and it works only as an intent classifier. And the baseline there also is just not more than 1 or 2 points behind what you have with transformers. So definitely sparse features are just looking at what are the words important for this intent and it's a good way to represent your input.
Okay, so there are three questions. Yeah, and uh, first question, which order should I? Diet. Okay, two questions about diet. How much annotated data do you require for intent and entries?
Sure, that's a very frequent question. So what we recommend within the diet algorithm, as what we have machine the model that we have, it's always good to have start with at least 30 to 40 examples under each intent. And we've seen improvement. We've obviously seen improvement in performance for more examples than that. But really, this is a very data set dependent, task specific question, in the sense that 30 to 40 is a good, maybe a baseline number to start with, but definitely I would encourage everyone to try adding more and more data, and we'll see in the presentation, in the talk, how you can do that in a more efficient way.
Yeah, and so yeah, adding data leads to this question, which is about uh, so the intents evolve with time,
Hmm.
as you. So, are there unsupervised intent extraction methods except plain clustering approach that will help you more easily evolve with time rather than training the classifier overnight?
Yeah, definitely. So um, it's I mean, as you said, clustering is basically one way to do it. The second way could just be something like topic modeling as well. You could use topic modeling as a way to just identify, different topics that are in your collection of utterances that you've maybe gathered from somewhere, maybe real user messages. The other ways could be something like what are so what I mean, so this is actually not a very explored area, but there's a very recent kind of representations that are coming up, which is known as semantic maps. And I'll not go too much into detail, but I would encourage you to look at them, and they really have some nice properties which can help you with that.
Yes. Okay. And the third question is deep into the diet architecture is other than pairwise similarity based training, we evaluate simpler training schemes for this diet
Yeah,
architecture.
definitely.
Jan.
So we definitely tried out a simple softmax similarity, which is the simplest strategy that you can do for supervised classification. What we definitely found was that this dot product similarity based loss definitely helps for in low data scenarios. It's able to and the one of the hypotheses that I have about it is softmax based losses always help, always try to um, you know uh, make your model overconfident about its predictions. And let's say if you're training it on low amount of data, your model would tend to be overconfident um, about representations that it has seen already, and that's not essentially a good thing to have when you want to generalize to a larger data set or real messages. And that's where we found that this loss was much more apt for this task.
Yes. And so there's similarity between the embedding of the mask and the last word, and then there's similarity between this class token and the intent. Right? They, both the similarities are working together.
Correct. Right.
Yeah.
Right. So one is being fed to the intent classification loss, and the other one is being fed to the masking loss, and then all three of them come together as a and then so it's like a basically a classical multitask learning architecture. That we
And do you know need both of them together, both the losses together, or intent losses? And does it, or well, if we can make both of them work together, it's that's perfect.
Yeah, I mean, what we found through results was that definitely entity recognition benefits a lot more through this architecture, because as I said, there are few specific entities that can occur in specific intents, and because of that, it's a good, it's always good to embed them through or extract them through one common model. But if you like, you can also build individual models for each one of them, where one of the laws is just turned off, and that's something that you can do through easy configurations inside Rasa open source.
Okay, thanks. Yeah, so it's great. We are having great questions, and our speaker is answering all of them. So we are having a wonderful time here. Yeah, I don't know how much we are in terms of time, and so
Yeah,
please.
sure. Let's. I mean, so we're at 60 minutes, and we can take a 5-minute break maybe, and maybe rejoin. And in that meantime, in those 5 minutes, I can definitely be online. And if somebody has any other questions, they can shoot some questions.
Sure. Um, well, I think it's a comment rather than question. NLI based or zero shot approaches can help. And then there is a blog pointer, which I'm not sure you can see that.
Um,
But yeah, for intent classification.
I can come to, yeah. So maybe NLI based or zero shot approaches can help. Yeah, that's definitely a good point. That can help you to get that can definitely help you to get to what possible intents are there in a new collection of utterances that maybe you've collected, right? So, but then I definitely feel you might want to curate them better, because this way you could have a lot of noisy intents as well, which can hurt the performance, the downstream performance of the assistant, right? Because remember that just natural language understanding is not your end goal, right? The output of this is being fed to your dialogue manager, and if this output is wrong, it's a very tough job for the dialogue manager to take the correct action for the assistant.
And then you can probably see a question just came in
Yeah,
from
so
Bhavesh.
for which type of entities do you recommend rule/dictionary based approaches? That's a good question. So what we found is that, so within Rasa open source, we have a couple of ways to do this dictionary lookup. And entities, I would definitely say entities where you might have a lot of synonyms for the same entity. So for example, you can have a name of a place with its acronym as well as in its full form that users can express, right? So, for example, Los Angeles, people can say LA or Los Angeles, right? What you can do is you can have a few examples where you only show the, let's say, the full form of Los Angeles and add that to your training data. And then what you can do is you can what we call as lookup tables, so basically, or synonyms essentially. You can define synonyms for Los Angeles and say that, hey, if even if you find LA, that's a synonym for Los Angeles. So that way you can integrate both of them. All right, so let me go back and go with the next part, which is, can we use data augmentation to squeeze more out of current models? And essentially, this question is more motivated from the use case again, which is when you're starting to build an assistant, it's not easy to do it because your users can express the same intent in many ways. And the question that we ask is, can we help an assistant builder just bootstrap their assistant with enough amount of data to start with? Right? And one way in which we feel is a good way to do it is, having a kind of a paraphraser where, you have an example input sentence over here. So for example, you have, I am searching for flights from New York to Berlin for next week. And then the job of this paraphraser is to express the same sentence in a few varied ways, where there is good amount of semantic similarity between the paraphrases and the input, but there is some amount of lexical and syntactical diversity. So for example, you can change I am searching to my search. You can bring next week before in the sentence. So this induces more amount of syntactic diversity, right? um, Before I go to what's the best way to build a paraphraser, I would like to touch upon how not to paraphrase, because this is very important. And one common way how folks do it is by using a rule-based script to really generate data like this, what you see over here in the screen. So the idea over there is you have a few templates where the templates have certain placeholders and certain optional parts within that template. And then using that template, you can essentially generate a lot of data by inserting your entities, using the optional part, not using the optional part. And if you really see over here, you've at this point you've written a grammar for your intent classifier, right? So you've the all of your examples are going to look very templated. You can maybe, if this is your task, you can maybe just do something like a rejects based intent classifier and get away with the problem, right? But the problem is, if you're really now building a machine learning model based on this data, your machine learning model is going to just mug up the templates, remember the and memorize the templates, and it's not going to generalize very well to real user messages. And that's why we feel there's a much more this is not the way to paraphrase, and let's explore what we can do better. So we take some inspiration from this field of multilingual neural machine translation. And just as a small segue, let's look at how multilingual neural machine translation works very quickly. So this is essentially one of the state-of-the-art architectures by Brian Thompson in 2020, where what they showed was you can have a classical encoder-decoder style architecture. You feed in a sentence on the encoder's side, and then your decoder should basically output the translation for the input in a particular language. And the way how you specify what language you want on the target side to appear is by adding a language ID token to the decoder at the start of generation. So you basically say, hey, I want to generate from English to Spanish, and that's when you basically input the Spanish ID token, and the model should start translating it to Spanish, right? Now, what's the reason why do we want to look at this? We essentially felt that multilingual neural machine translation is a good proxy model to use for paraphrasing. And the reason really lies in what recent work has shown around multilingual neural machine translations about what they really learn. And the basic intuition is very simple, that multilingual neural machine translations are just learning a shared semantic space across different languages, right? So you have the same sentence which can be expressed in multiple ways, and in multiple ways in different languages. And what we're trying to do is trying to come up with a shared semantic space which can represent it across these languages, right? And the second point is that there's no linear word alignment between two languages, right? So for example, in this example, if I had to translate I am paraphrasing to Spanish, the dumbest way would be, let's say, you take the translation for I, you take the translation for M, you take the translation for paraphrasing, and just output that. But obviously, that's not a natural or coherent way to do it, right? So what this makes us realize is that there's no word alignment, and I mean there's a word alignment, but it's not exactly linear, right? So the way how languages are composed are very different to each other. So it's unlikely, let's say, if we set the language token on the decoder side over here to the same language ID that we have for the input sentence, and we set it to the same language ID, it's unlikely that the output that the decoder generates is going to be always exactly the same. And this is essentially the hypothesis that we started working with. And the main work that we wanted to do was, let's say, if we have multilingual neural machine translation model, a large scale one like this, can we just explore the output space of the decoder to see if we can get out different variations of it, right? And the first thing that we started off looking at was what are different decoding strategies that can help us over here. And the first obvious choice comes out, beam search, right? So if you're familiar with generative models, beam search is one of the classical approaches to generate information from generative models. The idea is simple. At every time step of the decoder, rather than outputting just one token, you output a candidate set of tokens. And then for each candidate token, you further keep generating more candidate tokens at subsequent time steps, right? So you, in some way, you have some beams that you're exploring for the decoder, right? And the problem with beam search is that the output of beam search itself just lacks diversity, in the sense that, yes, you're exploring different options, different candidates, but at the same time, you're not optimizing for diversity explicitly, right? And there's this, so just to mitigate that problem, there is a variation of beam search which is called diverse beam search. And this was proposed by Vijay Kumar and their group. And the idea is simple. You take different groups of beam search. You basically divide your beam into different groups, and each group is optimized to output uh, lexically diverse outputs. So you can take, so basically what you do is, in the objective function, you add an explicit constraint that each group should be, let's say, there's a cost that you add, which says that you want to explicitly penalize outputs where groups are very similar to each other. And the cost can be as simple as something like Hamming distance or edit distance between pairs of sentences. And what we found, and in the interest of time, I'll skip a few slides, but what we found was that in general, neural machine translation in combination with diverse beam search works well for paraphrasing. So here are some of the examples. Let's say for English, one of the example sentences is, how can I reduce CO2 emissions? And it came up with a few different variations to represent it by saying, so for example, just saying, can I reduce CO2 emissions? But how can I reduce CO2 emissions? The question is, how can I reduce CO2 emissions? Is it possible for me to decrease our CO2 emissions? So these are some nice different candidates that you can pick up. Similarly, for German and French, we saw that it's able to generate some good amount of diversity. And of course, we wanted to put it to test on the downstream task, which is of intent classification, let's say. And what we did was we took a intent classification data set in German. We tested it for different languages, but this plot shows you for German. And so we took 10% of the training data and tried to paraphrase examples for it through our paraphraser, and just augment examples into the training data and test it on the complete test set. So the dotted lines that you see are the performance of the intent classifier without any augmentation. The different colors represent different featurization pipelines within Diet, as we saw. And the solid lines basically show you what is the performance gain that you get with a paraphraser-based data augmentation. So the x-axis shows you the amount of paraphrasing that you've done, or amount of augmentation that you've done, and the y-axis is essentially the F1 score for intent classification. And yeah, so this was a good result to see that, yes, specifically in low data scenarios, because mind you, this is just 10% data. So this whole data set was around 800 examples. So 10% is essentially 80 examples spread across 20 intents, which means you're starting off with, let's say, just almost 4 examples per intent, and you've tried to paraphrase just those 4 examples in different variations and see how much you can gain for on the test set. And because we made this point that you shouldn't use rule-based scripts, we really wanted to test that as well. So we took data from an already existing assistant, which is called Financial Bot. And so we took 250 examples as the original data. We took some of the real messages that users have actually expressed while talking to the assistant and constructed a test set out of those. And the F1 for the original data is 0.73. And then what we did was we added 10x amount of data using some rule-based scripts. And that gives us an F1 of 0.75, really not a huge boost for the amount of data that you're adding. And then we used a paraphraser based approach for adding more synthetic data. And that gave us around 0.84 as the F1. So this is this is one example, one data set, but this has really been consistent on a lot of other data sets as well. One good thing is, so this multilingual paraphraser would be out as inside Rasa open source as a separate open source library very soon. So yeah, really looking forward to how people want to use it for different tasks as well. All right, so the third learning is just do not generate data with a rule-based script. Please, if you're doing that, you're writing a grammar for your intent classifier at that point. If you really want to help yourself with more data augmentation, use some more evolved strategies for that. Any questions at this point?
Yeah, so I think you just answered that it's going to be open source pretty soon. Hello? You lost again. I think.
I'm still audible, right?
Okay, we are back. Yeah, there was a connection.
Oh, there was a connection error, is it?
Yes.
And where did I leave off?
Yeah. So could you again share your screen? I don't know if I missed something between, but multilingual paraphrasing, are you going from English to another language and then coming back and then using this diverse beam search? Or is it you? How is the paraphrase actually happening?
No, so what you are basically saying is what is known as round trip translation. Round trip translation basically adds an additional intermediate step in between, where, as you said, basically you would try to first go to a intermediate pivot language. Let's say that could be English for you, for other languages, and then from English you would translate to other languages. But a lot of state-of-the-art multilingual neural machine translations now do a direct translation for the pair of languages given. So, for example, if you want to go from French to Spanish, the same model can help you do that directly without reaching to an intermediate space.
Yeah, so sorry. So my question was, you want to go from English to English, right?
Correct.
So, I'm still trying to place a multilingual translator in the path from English to English.
Sure. So basically, what the simple trick that we did was replace the target language ID token over here with the same language as of the input. So it's not necessarily just English. It can be any language on the input side. You essentially use the same language ID token to prime your decoder. And one way to think about this is that the one reason why the language ID token is placed over here and not on the encoder side is that you want your encoder to be as language agnostic as possible. And you want this shared embedded space across languages. And then once you have the representation for the input sentence, you then want your decoder to be primed with the target language and start your generation at that point in time for the target language, right? So we essentially simply just replace this language ID token with the same language as the input to basically use it for paraphrasing.
Yeah, and if I may ask, if you just took a paraphrase data set on English and you
Yeah.
trained this encoder decoder on that, and then you use beam search, will that give worse performance than using a multilingual translator?
Yeah, so the problem is there doesn't really exist a lot of paraphrasing data sets. There are some, and they're very noisy. So one of the first English paraphraser that we built was trained on a 5 million corpus of paraphrase pairs of paraphrases,
Mm-hmm.
but it was such a noisy data set, and we basically what we did was we fine-tuned GPT-2 on it, and really the kind of paraphrases that come out are not very they're very noisy as well, I would say.
And this multilingual scheme lets you use a lot of data of different languages, and then you go back to the same language. So it's
Correct.
pretty nice trick. Yeah, it's a very nice trick. Yeah.
Yeah.
There
All
is
right.
one question. Sorry, is Diet's performance on Indian languages? Do
All
you have
right.
any thoughts on that?
Um, we've done a couple of benchmarks for Hindi, I would say, but it's always data set dependent. So I mean, I could give you numbers for a couple of Indian data sets, but it the performance might vary. So I mean, look, the trick really there is, as long as you have a tokenizer for your language, which is, let's say in this case, Hindi. So you want to, I mean, Hindi can be tokenized at white spaces as well,
Mhm.
right? And then you can use the sparse features and, let's say, some word embeddings, which are like maybe BERT embeddings or any other embeddings, and just featurize through that. I think the performance should be very much comparable. Of course, data set is dependent, but then it shouldn't be very degrading just on a language. I mean, the performance should not depend on the language, I would say.
Yes. Okay. Thank you. Yeah.
All right, so that brings us to the last part, which is, how do I really improve my assistant over time once I've deployed my assistant? How can I put in a process where the assistant can learn itself from real user messages and improve itself over time? And again, the motivation is again the same. We established this, that anticipating what your users will say is going to be hard, which is essentially the problem that you start with when you start building an assistant. But let's say if you've shared your assistant with some early users, they're essentially telling you, I mean, your users are telling you what they want to express to the assistant and how do they want to talk to the assistant. So there should be a process in place where you just listen to them, collect the data, and just improve your assistant from it. And that's exactly what we call as conversation driven development. And that, let's see what conversation driven development is all about. So it's composed of 6 steps, and these are the steps that I
So
made. So
we
let's go
have
into.
lost the screen. Can you share again?
Okay,
This is something strange.
it shows to me that I'm sharing my screen, and now I'm trying to share again, but it doesn't let me share it now.
Okay, so that
Now I can
is a
click on.
report about time. This is a relatively new platform, so I don't. But yeah, I mean, if you can't, is there a
Let
way
me
you can
let me let me log back in really quickly,
refresh
and
the
maybe that
browser?
helps. Yeah. All right. Now I think it should work. Okay. Can you see the screen now?
Yeah.
Yeah. So basically 6 simple actions for conversation driven development. Let's see each one of them. The first step, please share your assistant in its early stages to some of your test users. I mean, as we established, it's hard to anticipate how your users are going to talk. And users will always surprise you while talking to your assistant in terms of how they want to express themselves. A simple example is, a lot of times real users do not talk to the assistant in well-formed sentences. So for example, let's say if I want to request for if I want to apply for a new passport, then I would just say new passport, and you will find users like that, right? And your training data might have really nice well-formed sentences around this query, but maybe the intent classifier just fails because the distribution is just not the same, right? So it's always helpful to share your assistant, collect those messages, and see how they're talking. Once you've done that, it's important to then review those conversations and messages. So on the right hand side, what I'm showing is the screen of our product called Rasa X, which is essentially this product where you can now hook your assistant to Rasa X. You can and then Rasa X collects all the conversations that your assistant has had, and then it shows you what are different messages that people have sent and what are the predicted intents for them. So you can now look at the screen, annotate. You can basically see what have they messaged, and actually also annotate the correct intent if the existing intent classifier has made a mistake. And yeah, just annotate more data through the whole process of reviewing. And as I said, please do not use a script to generate more amount of data. Just use real examples and turn them into training data. Yeah, fourth point is a very important one, which is testing your assistant. So, I mean, just drawing parallels with how usual software development works, you have a lot of tests in place to, like, for example, unit tests, integration tests, to see if before shipping out your code, you know that your code works as intended, right? It's the same for conversations as well. You can always have end-to-end conversations which are acting as tests. So essentially, you can have a CI service where you are running your assistant on these test conversations, and your assistant should only pass if all of these test conversations are perfectly executed by the assistant, right? So having this in place will always help you out. And I mean, there are a few recommended approaches around how you can do this for Rasa open source. You can check out the blog, our blog too, for that. And yeah, this is also another very important thing. So once you have your assistant deployed, there are different proxy measures that you can track to just measure what is the success rate of your conversation. So for example, let's say you might have let's say your flow of your assistant could be that at the end of the conversation, you want the user to click a particular link, and that might be a proxy for just measuring how many conversations were successful. Because if that click didn't happen, it is very likely that the user could not even reach to that stage, and which means that the conversation broke down somewhere, right? So come up with metrics like these to track once you're confident of your assistant. And then of course, study all the conversations. There might be intent, there may be some problem with the intents, there might be some problems of how dialogue manager is working. It's always a good idea to just look at those conversations again, fix them, and more importantly, add those conversations back as tests, right? And by that, just fixing issues with other with conversations that just didn't work before, right? And in practice, really, this is not a linear process per se, in the sense that when you're practicing CDD, you will find yourself jumping between these actions. So you might first share your assistant, and then in the process of that, you may keep reviewing some messages, and then while you're reviewing, you may feed it to your test server and see if the assistant improves. If it doesn't improve, you will come back, annotate more, again test, track some measures, track some metrics, and then so it's, don't look at this as a linear process. There's no sequence of steps. You will constantly be jumping between these actions. And essentially, because we advocate for CDD so strongly, here's a evaluation for it. So the same financial bot that we showed performance for it on for paraphrasing, what we did was, we also annotated some real user messages in addition to the original 250 examples that we had. And these messages were different from, I mean, completely separate from the held out test set real user messages. And as you can see, it helps you go from a 0.733 f1 to 0.93, and no amount of synthetic generation can help you achieve that. So yeah, that gives us basically the last point: practice CDD. That's really the best practice while building task-oriented assistants. That will definitely ease out your complete workflow. The last general note that I want to leave out with is NLP dialogue is still hard. It's not a solved problem. And I would encourage everyone to please contribute into open source, and start making progress collectively, because it's, I mean, this is from my experience itself. It's amazing to see what people can do with something that you put out in open source. And it will always surprise you, right? I mean, and this is what as an example, this is what I'm looking forward for Paraphraser. I mean, we've tried Paraphraser for intent classification. I'm looking forward to what people will do with it for other tasks. So yeah, just as a last message, start contributing to open source if you're not doing already, and that would help progress the field of conversational AI forward. And with that, I'm happy to take any questions. I think I overshot the time already, but maybe we can do some questions if folks are interested.
Yeah, that's not a problem. Thanks a lot. This was an amazing, very informative talk, and I guess for most of us, yeah, all of us learned a lot. If there are any questions, please ask. I think there is an older question that can we do diverse beam search, based paraphrasing with self-supervised training-based model?
What do you mean as self-supervised over here? So, I mean, if the user is live right now, do you have a clarification on that?
Says bird-like model.
I mean, it's then, I mean, are you saying that you want to do then something like, you want to actually paraphrase, you want to keep paraphrase as your end task and train a supervised model for that? Because if you're doing that, as I said, paraphrasing corpuses are not in plenty, and we're really using neural machine translation as a proxy task for paraphrasing, right? So I mean, if I don't know if that answers your question.
Yeah, I think it's all mixed up, right? It is all half BERT-like model. I mean, transformer layers are there, but BERT means this masked LM objective, which is not related to paraphrasing. So, okay.
I mean, okay. So I think I get what they're trying to say. So, well, I mean, the supervised, the subset, I mean, just the way how multilingual neural machine translations are trained are essentially by mining pairs of sentences across languages, right? And then just collecting a plethora of languages together and examples for them together, and training one model for them, right? So in that sense, if that's the way how you're generating your corpus, your end task is machine translation, you could say that yes, it's a self-supervised way of training your model. It's already a self-supervised way of training your model then, right? Um, I mean, the self-supervised task could be different if you want, but I don't see why not having a translation objective will be any different or would be better. But happy to hear any opinions on that.
One question that I thought of was that when you deploy these things live or with interact with real users, one of the issues is that you get improper sentences all the time,
Hmm.
half sentences, and so fixing the vocabulary, fixing the grammatical mistakes, completing the sentences so that your intent classifier passes correct your entities. So, I mean, it seems it's always seemed to me that there should be just a module which does all the grammatical corrections, and then the rest of the flow starts. Is my view correct? Is there a generic? I mean, one could have a generic multilingual module which does this grammar correction and for once and for everybody, so that everybody doesn't have to build. But yeah, you probably see where I'm going. So, what is the
Yeah.
state right now, and what is yeah,
The way how I look at it is that each of these smaller NLP tasks that you just mentioned, even fixing grammar, even trying to expand
correct?
non-well formed sentences to well formed sentences, all of these are still unsolved tasks at this point, I would say, right? So the even if you want to use a pre-trained model for these tasks and use these as pre-processing modules in your assistant, there's still no guarantee that it would work, right? So it's better always to just have more control on it by adding data yourself, which is more representative of how users are talking, and that's exactly where CDD comes in. Then
Nice.
I think there's something on.
Snorkel for CDD.
Yeah, we've been looking at Snorkel. So, for everybody's benefit, Snorkel is this framework where using weak supervised learning, and weak supervised learning is where you essentially define a few rules for annotation. So, you take, so basically, your rules can be if there's this keyword present, then this is the intent, or if, let's say, if the sentiment is this, then this is the intent, right? So now, combining all of these rules, you can annotate a data set with some noisy annotations, and then the idea is that can we train a model using these weak annotations, weakly supervised annotations, to help. um, I mean, we haven't compared snorkel based approach with CDD, to be honest, but again, I think what will end up happening for snorkel also is that you still have to write your rules for annotation, right? Now, if you're writing rules for your annotation yourself, then again, you're not listening to your users, you're still coming up with your rules yourself, right? So I don't see exactly how those two align over there. But definitely, I agree that there would be a good that would be a good evaluation to do, and see if there are some opportunities over there.
It's awesome. Yeah, if the
Mhm.
quickly, if there are any more questions. Sorry, were you saying something?
No, no, I'm just saying thanks. That's all.
So thanks everybody. Is there a way to get the slides? Yes, Daksh will be sharing the slides, and I'll post it on the LinkedIn event for this. And yes,
Yeah, thanks everyone for taking out the time. And yeah, lovely speaking to everyone. I mean, you can reach out to me on LinkedIn, or I put out my email as well. And I just put out my email over here as well. You can reach out to me over here if you have any questions or just want to discuss about anything else. I'm happy to have any questions. Thank you.
okay, thank you everybody for joining. Thanks. We'll have some more such talks. So follow OffNote Labs. Stay updated. Thanks again. Thanks, Dash, so much for
Thank
this wonderful
you.
talk. Yeah,
Bye.
yeah. Thank you. Bye bye, everybody.